this class. Class now is recorded. Who wants to go first?
Can I go first, please?
Oh, sure, Emma. You always want to go first.
Yes.
Go ahead.
Thank you. Okay, allow. All right. So can you see this?
Yeah.
Okay. So the question is, 3 prisoners are informed by their jailer that 1 will be executed and 2 freed at random. Prisoner A asks jailer to tell him which of the other 2 is free, since he knows at least 1 of 2 of them will be free. The jailer refuses because if A knew which one was free, his own probability of execution rises from 1/3 to 1/2. What do you think of jailer's reasoning? So I thought to make it an instance that like we pretended that the jailer said B was free because like we talked about last class, I think it was called Bayer's, something like that formula. So I'm going to create
formula.
yeah. So that's a hypothetical. So my hypothetical is that B is going to be free. So I used it as reference and created my own formula with this information. And then what I needed for the information was if A was to die, that means that the jailer would have said B or C is free. So that gives B and C 1/2 out of 1 total that they're told that they're free. Then if B dies, obviously B can't be free because 1 out of the 3 is going to be executed and the other 2 are going to be free. And then if C dies, A is definitely going to be told they're free, and so is B because only 1 person is being executed. This is a very dark problem, but I thought it was interesting. And so I inputted the amounts that I came to, and I also put 1/3 because it's 1 out of 3 people. So for each of the instances, the probability of them dying would be, what I found. So then I found that it's 1/6 over 1/6 plus 1/3, which ends up being 1/6 over 1/2, which is 1/3. And the jailer had originally said that the probability of the execution rises from 1/3 to 1/2. But this proves that the jailer was wrong, and he probably should have told A what was going to be happening.
Very interesting question.
Yeah, I thought it was really interesting too.
Yeah. Good job. Anyone has any questions? Great. Thank you.
Thank you.
I'm going over chapter 3, question 20.
Okay.
A total of 48% of the women and 37% of the men who took a certain quick smoking class remained non-smokers for at least 1 year after completing the class. These people then attend a success party at the end of year. If 62% of the original class was male. First of all, I set out variables for like W for women, M for men, and P for the attend the success party. It gives that the male is 0.62%. It's 62%, so I got 0.62. And then I found that woman by using the whole probability of the man and woman will be 1. So I use 1 subtract 0.62, get 0.38 for for the woman, and give that the party attend of women it's 0.48, and for men is 0.37. And for question A, what percentage of these attending the party were women? So is the probability of women W/P. So I use this one, the probability of women times the percentage of party that it's being a woman and attending a party is a woman, and and add up the total numbers of the party is a woman and a woman, then the party is a man and man to get this one. And they want to be like the percentage. So I multiply by 100 to get 44.29%. And
Okay,
for
good.
B, I want the numbers of the attending the party. So I just like get the party as attending as a man times man plus the party attending as a woman and woman, and get 0.44118 then times 100 to get 41.11 as a whole percentage.
Okay, yeah. Okay, for the presentation purpose, next time just write down the intermediate step. Let's see for A, right? Probability of a woman who's in the party is a probability of the people in the party multiplied by probability of P/woman in the party. So write the
Like this one,
intermediate step.
you mean?
For A and B, did you read? Yeah, like a B, exactly. So this way you show exactly what's going on, or what the number is. But it's good, very good, very interesting questions, good. All right, great. That's how. Okay, if anyone has any question, feel free to jump in. We're learning together, all right? Because everyone picks different questions. This is great. How? Okay, they're here. Have we done? How? Okay, who's going next? Okay, Darius? Yes, go ahead. So I had hello, what's going on?
Is anyone going? If not,
Yeah, anyone can go, because you're ready. Just click a share button, whoever screen.
can you see my screen?
Yes.
Okay. So, with probability 0.6, the present was hidden by mom. With probability 0.4, it was hidden by dad. When mom hides the present, she has it upstairs 70% of the time, and downstairs 30% of the time. Dad is equally likely to hide it upstairs or downstairs. So we have the probability. So I just interpret all those to here. So probability of mom hides a present would be 0.6, and that is 0.4. And then for upstairs given mom would be 0.7. Upstairs given dad would be 0.5. And then downstairs given mom would be 0.3. Downstairs given dad would be 0.5. For part 8, what is the probability that the present is upstairs? So we're looking for the probability of upstairs. That would be just P of U. And we expand it, we got P of UM plus P of U component of M. And that would be equivalent to P the probability of U intersect component of M would be equivalent to the probability of upstairs intersect that. And we just plug in those value. But before that, we gotta change our expression to this,
Right.
to those two, and then we just plug in the value. For the upstairs given mom would be 0.7, and the mom would be 0.6, and upstairs given that 0.4, and that would be 0.5, and the final answer would be 0.62.
Yeah.
For part B, given that is downstairs, what is the probability it was hidden by that? So we know it's downstairs first, and then that be that given downstairs. And then we can just extend it. We got this, and then just further expand it. We got those, and we just plug in those values. And
Great.
we got,
yeah. So right, so these notations are good. So each step just shows the notation. This is a probability, you know. If we can do this, we can interpret the question and use the right notation, use the right formula. You know, we're done. That's probability. Great job. Good. And so you use UC, the complement of upstairs, which is downstairs. I see. Okay, great. Anyone has any questions? Okay, so that's Jie.
thank you.
Thank you.
Hi, Professor.
Yes. Hi, Catherine.
You see my screen?
Okay. Yes. Very clear.
All
Wow,
right,
you have such a
let me
neat
know.
handwriting. Is it handwriting?
Yeah, thank you. Yes, my handwriting.
Wow. The
Can you hear me
like
clear?
printed. Yes, please.
Can you hear me clear? Okay.
Yes, you're good.
So I'm presenting question 38. So stores A, B, and C have 50, 75, and 100 employees respectively, and 50, 60, and 70% of them respectively are women. Resignations are equally likely among all employees, regardless of sex. One woman employee resigns. What is the probability that she works in store C? So I added all the employees together. For our sample space would be 225 employees. And I noted event 1 is store A, event 2 is store B, event 3 is store C. And then I get the probability for like event 1 is 2/9, and probability of event 2 is 3/9.
I have a question,
and
Catherine.
Catherine,
can I have a question?
Yeah.
Why you didn't choose to use ABC to represent the events?
Oh, I just like it that way.
You like why? Okay, go ahead.
Yeah. And then event 3 is 4/9. So since we know that I let R to represent event that a woman employee resigns. So for store A we get like 50%, B and 60%, C 70%, because only one woman resigns, so we just multiply by 1. And then for the probability that, and then when we multiply and add them all together, for the probability that a woman employee resigns from all of them is 28/45. And then we scroll down, we use Bayes' theorem to calculate the total probability that she works in store C. Yeah, so this probably that an employee resigns from store C is a woman that's 50%.
Yeah. Okay. All right. Can you explain the Bayes theorem you applied?
Oh, so the woman employee that resigns from store C as a woman is equal to P, and then from it we use, because we're using from store C, so that's event 3, and then we use the formula for store C that a woman resigns times the event 3 from store C, and then we divide the whole similar space to get 1/2.
Yeah, this is very interesting. So this one formula includes actually 2 formulas in it. Yeah, that's all about probabilities. Just use the formulas. Great. Okay, good. Good job. Anyone has any questions? Thank you, Catherine.
Good evening, Professor.
Good evening.
Can you see my screen?
Yes, 秀云.
Yeah.
秀玉.
Yeah.
Okay.
So I'm going to present question number 18 in chapter 3. So the question is, in a center community, 36% of the families owns a dog, and 22% of the families that own a dog also own a cat. In addition, 30% of the families own a cat. What is A, the probability that a randomly select family owns both a dog and a cat? So in here, I use D to represent the events of family own a dog, and C to represent the event of family own a cat. By the question, we know that the probability of families own a dog, which is 36%, is equal to 0.36, and the probability of family own a cat is equal to 30%, which is equal to 0.3. Then we also know that the conditional probability of a family own a cat given that the family own a dog, which is 22%, is equal to 0.22. Then by the conditional probability formula implies that the probability of both dog and cat, which is equal to the probability of cat given dog times the probability of owns a dog. So it's equal to 0.22 times 0.36, which is equal to 0.0792. And question B, the conditional probability that a randomly select family owns a dog given that it owns a cat. In this question, we just use the conditional probability formula that the probability of owns a dog given that owns a cat is equal to the probability of both dog and cat, which we proved in question A, is equal to 0.0792 divides the probability of owns a cat, which is 0.3. So the final answer is 0.264.
Great. Anyone has any questions? Good. Good job. 秀玉. Okay. Thank you. Next one. Okay. 音频.
Oh, hi.
Hello.
My question is 17. The question is 98% of all babies survive delivery. However, 15% of all births involve cesarean section, and when a C-section is performed, the baby survives 96% of the time. If a randomly chosen pregnant woman does not have a C-section, what is the probability that her baby survives? I said A for the baby survives and B for the event has cesarean section. And we have some information for PA is 98%, PB is 15%, and PA given B is 96%. And for B complement is 1 minus PB is 85%. So for question, we need to find the probability of A given B complement. Based on the formula is PAB complement over PB complement. We use the formula for the first one. We can get the probability for A intersect B complement is equal PA minus PAB, and PAB equals to PA given B times PB. So the final is final. We have all the information from the question. So the answer is 80%. 98% minus 96% times 15% over 85% equal 418 over 425.
Okay, great. So again, you see probability theory just to know which formula to use and to interpret the English words into the correct term. But I would suggest you to use C-section because usually, the cesarean section just called C-section. People just call C-section. You could use P of C to present
Okay.
C-section. Okay, great. Thank you, 音频.
I'm presenting 3.7.
Okay.
The king comes from a family of 2 children. What is the probability that the other child is his sister? So S is the possible outcomes, which is boy, 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 girl, girl, boy, and girl, girl. So let B be the event that of the 2 children in the family, there are at least 1 boy. So B is boy, girl, girl, boy, boy, boy. And the probability of B is 3 over 4. And let A be the event that of those 2 children, there is a girl being the king's sister. So A is boy, girl, or girl, boy. And the probability of A is 2 over 4. So the probability of A and B is 2/4. So hence the conditional probability of A and B is 2/3.
Such nice handwriting.
Thank you.
Okay, great. Yeah. If anyone has any questions, feel free to jump in.
Hello, Professor.
Hello.
I'm going to present question number 21 of chapter 3.
Okay.
52% of the students at a certain college are females. 5% of the students in this college are majoring in computer science. 2% of the students are women majoring in computer science. If a student is selected at random, find the conditional probability that. From this case study, we get the data. Number of female students, which are 52%, so we get 0.52. Students are majoring in computer science are 5%, so we get 0.05. Female students are majoring in computer science, which are 2%, 0.02. So the part 1, which we have to find, the student is female. given that the student is majoring in computer science. So for this, we have a conditional probability P female and computer science, probability of female and computer science. We have the formula of this thing is probability of female computer science over probability of computer science. We have given that the probability of computer science is 0.05 and the probability of female and computer science is female students are majoring in computer science which are 0.02%. So from this calculation we will get 0.4 answer. For the B part, we have the question. This student is majoring in computer science given that the student is female. So for this part, we have probability of computer science and female, which is equal to probability of computer science um, given female over probability of female. Probability of computer science and female is 0.02%. Female students are majoring in computer science, which are 0.02, which is equal to 0.02 over the total female numbers are in college, which is 0.52. After this calculation, we will get 0.03846.
Okay, so Ikara, what's your major?
Yes, Professor.
What's your major? What do you major in? Your
Professor,
major in
financial
computer science?
mathematics. Financial
Financial mathematics.
mathematics.
So okay, so maybe get into a habit, because you don't want to write this all the time. Get into a habit of
Yes,
using
Professor.
notations. So first you define your notation, then you use your notation. All right.
Yes, Professor.
Okay, but it's good. Great. All right. Very clear. Thank you.
Thank you, Professor.
Hi, can you guys see my screen?
Hold on 1 second. Yes.
Okay. So this is chapter 2, question 20. So the question is, suppose that you're playing blackjack against a dealer in a freshly shuffled deck. What is the probability that neither you nor the dealer is dealt a blackjack? So cards 2 to 10 are as marked. The king, queen, and jack are worth 10 each, and the ace card, which is an A, is 11. Both the dealer and the player are both given 2 cards. And blackjack is exactly 21, meaning that you need an ace and a 10 value card, which is either a 10, king, queen, or jack. So situation A is the player gets a blackjack, and that is achieved by the number of aces, which is either 4, and the number of cards remaining at a value of 10 is 16 in the deck. And situation B is the dealer gets a blackjack under the same conditions as A. So that brings you to the probability of A equals the probability of B, which is 2 times 4 times 16 over 52 times 51. And you also get the probability of the union of A and B, which is 4 times 4 times 16 times 3 times 15 over 52.
Catherine, the intersection, which
Yes.
means A and B, right? Probability
Yes.
both in A and in B. Okay. Yeah, keep going.
Sorry, I forgot where I left off. 52 times 51 times 50 times 49. So that brings us to the probability of A plus the probability of B minus the probability of the union of A and B, which is
the intersection. The intersection. So
the
the first one
intersection.
is a union, right? The first one is a union. So you're trying to find the probability of A or B.
Yes.
A or B, right? So the subtraction is subtracted the A and B.
So that gives you 2 times 4 times 16 over 52 times 51 times 2, because there's 2 players, minus 4 times 4 times 16 times 3 times 15 over 52 times 51 times 50 times 49, and you get 0.0948.
Okay, interesting question. All right. So that's 9%. All right. Okay. All right. Okay.
Sorry, I was a bit nervous.
Oh, I know. This is your first time, right?
Yeah,
it's good. It's good. Keep going. Next time, maybe go a little bit slower.
Yeah, sorry, I was nervous. I was just trying to get it over with.
Okay. Next time, let's try to enjoy it. Okay. All right. So I have whom left? I have Andreli. I have Tom. I think only you two. So this is Tom by the handwriting.
Yep. Okay, so for this problem, we're given probability of a person making more than 250,000, which is 1.3% of all U.S. households, and we're given probability that they're from California, which was
Hold on one second. Is this true? 12%. 12% of all U.S. households in California. Is that true? 12%?
It's one of the
Wow.
one of the 3 largest states in the U.S.
Oh, okay. Interesting.
Yeah, and it has an interesting result. So we're finding probability that a household makes more than 250,000, given that they are not from California. And so we use the identity, I highlighted it in purple, where we take the probability E equals probability E given F times PF plus P E given F complement times PF complement. And once we just use those, arbitrary variables, you just pretty much isolate for the part I highlighted in yellow, which was probability 250K given California complement, which is all non-California households. So once you isolate it, it's just a matter of plugging it in, and we get about 1%.
Okay, hold on one second. I like this one you highlighted in purple color. Yeah, that's so good. The second one, so probability of non-Californian. Hold on. Okay, I cannot make this larger. And also makes 250K above. What is in this? 1.3 over 100. What's that?
So that was given.
That's 1.3% of
all U.S.
Yeah. Right. Non-Californian. Okay, I see. The minus. Is this minus? I just want you to explain this.
Oh,
can you see my highlight?
Yeah, so we're just isolating for the yellow term. So
okay, I got it.
Yeah. So,
okay, you're just calculating because all this you plug in all the knowns. Is only this one is unknown, so you're just doing calculations here. Okay, got it.
Yeah, there's only one unknown.
Okay.
Everything else was given. For part 2, we're asked for probability of that, given that they make 250K, is the probability that they're from California?
Californians. Okay.
Yeah. So this is Bayes' theorem, and it's highlighted in pink. And we have to actually sort of modify it by multiplying the denominator on both sides so that we can get the yellow term, the numerator of the yellow term, which is the intersection of California and 250K. Since we're not given that explicitly, we have to sort of rearrange Bayes' formula to get it. That's how I got the numerator of probability California times probability 250K given C. Yeah, so basically to find the intersection, you just multiply the the condition element times the denominator in Bayes' formula. So once you
Yeah.
plug
So
terms in, you get about 30%.
that's extremely high.
Yeah,
Oh my.
I imagine it's because of all the like Silicon Valley tech people.
Oh, wow. Wow. Okay. Yes.
Yeah.
Silicon Valley. Yes. All right. Okay. Great. Anyone has any questions? Okay. I think Andrili is the last one. Good. I really enjoy your presentations, guys. Andrili 45. Yeah. Go ahead.
Anyone did 45?
Oh, I won't be able to tell the number, but once your problem is up, I can tell you.
Okay. Question 45 says there are 3 coins in a box. One is a two-headed coin, another is a fair coin, and a third is a bias coin that comes up heads 75% of the time. When one of the 3 coins is selected at random and flipped, it shows heads. What is the probability that it was the two-headed coin? Let H be the event of getting a head. And 3 coins, so we use 3 events. So the required conditional probability of getting the two-headed coin, given that the event H has already occurred, is given by.
Hold on a second. Hold on one second, Angeli. What is the ABC? Even ABC. Oh, H is the event of getting ahead. Even ABC. What are even ABC?
I don't know. I was rushing. Two-headed coin, fair coin, and the biased coin.
Oh, okay.
So the probability of B given H as a head is PH of B multiplied by P of B all over PH of B by P of B plus PH of A by P of A plus PH of C by P of C. And PH of B is 1 multiplied by 1/3. It's 1/3 chance over 1 by 1/3 plus half by 1/3 plus 3/4 by 1/3. Since it's 3 coins. And I just calculated.
Where did you get 3? What's 3/4?
That's the 75%.
Oh, 75%. Yeah. Okay.
Yeah.
Yeah.
Right. And the 1/3 is 3 different coins.
Okay.
The half is the fair coin.
Right.
The 3/4 is the.
So what is a two-headed coin? Two-headed coin means the back and forth, front and both heads.
Yes.
I see. Okay, got it. That's why you have 1.
And
so
then,
in the end, what's your answer? Yeah.
Yeah. 1/3 over 1/3 plus 1/6 is 1/4. The lowest common multiple of 3, 6, and 4 is 12. So 1/3 of 12 is 4 12s. 1/6 of 12 is 2 12s, and 1/4 is 3. 4 plus 2 plus 3 is 9. And 1/3 divided by 9 over 12 is 4 over 9.
Wow. Big probability, 4 over 9. Okay, almost 50%.
Yeah.
All right. Anyone has any questions? So Tom and Julie, that's it, right? Everyone has presented. And
I haven't gone yet.
oh, sorry. And that's one. Oh yeah. Oh, there is your first time, isn't it?
Yes, this is my first time.
Okay, and set it. You know how to share your screen?
Yes, I'm uploading a picture now.
Okay.
Okay. All right. Okay, so yeah. All right. So yeah, this is doing chapter 2, number 2. I had chapter 3 planned, but those my problems were taken. So pretty much what I have at the top is I'm representing each session by the number of hits per session. So 0, 1, 2, or 3. Then with that, I'm creating the sample space. So because you have to get 3 hits in a row, that would be the end of a session. So you have 3 by itself, because if you get it on the first session, then you get 3 arrows on the first 3 rounds, then that's the end of the session. So 3, 0, 3, 1, 3, 2, 3, so on infinitely. So then the problem also asks for an, where n would be, so for more than, so if n equals 1, then it's going to be for more than more than 1 session. So a1 would represent 2 sessions or more. Okay, and so a2 and so on. So the problem is basically asking, so determine the infinite intersection of an where n equals 1. So determine that this is going to be a descending event. So A2 is a subset of A1, A3 is a subset of A2, and so on. And so I determined that this infinite intersection is going to be the null set, because there's not going to be any element from A1 infinitely where there's going to be an element shared among all of them.
Hold on 1 second.
Mm-hmm.
No element. Oh, okay. So your answer is it's an empty set.
Yes, the empty set.
Okay, I see. Cool. Okay, great. All right, thank you. Anyone has any questions? Interesting. You guys are teaching me. All right. Okay, let me give you credit so I don't forget, because that's your first presentation, right? Now keep going. Okay, yes. Keep doing this. Let me see. So Arette and Chanel and S, Jaden, Raw, Reuven, Zakia. What about you guys? Prepare to present next time, okay? Okay, so today I'm going to talk a little bit. Let me see if I have opened this. Yes. Okay. So last class we talked about Bayes formula, and so far you already see the pattern of probability theory. Oh, I think I did too many. It's loading very slowly. Oh, okay. All right, so last class we talked about Bayes' formula, right? And today we have seen some examples. You know, some of you have presented to use to apply Bayes' theorem, which is great. All right, and so today, yeah, someone presented some questions similar to this. All right, so today we're going to talk about a little bit about independent events. Independent events. Okay, let's just read this. The previous examples in this chapter show that P of conditional probability, right? F event happened already, and we want to calculate the probability of event E happens after F happened. The conditional probability of E given F is not generally equal to P of E, probability of E, unless they're independent. If the two events are independent, that is true. But for conditional probability, the thing E depends, have some, you know, depends on F. So F happens has an effect over E. So in other words, knowing that F has occurred generally changes the chances of E happens. In the special cases, P probability of E given F does in fact equal to P of E. We see that E is independent of F because F has no effect on E. That is, E is independent of F if knowledge that F has occurred does not change the probability that E occurs. So we have this formula. Oh, I cannot highlight. Why can I highlight? I could highlight this. So the probability of E given F equals the probability of E and F, right? The intersection, we can ignore the intersection notation. Probability of E and F happens over the temporary sample space probability of F. It follows that E is independent of F, so we have this, right? We have a probability of E and F equals the probability of E multiplied by probability of F. Okay, so if it's a dependent, we have probability of E and F equals to probability of F multiplied by probability of E given F. But if they're independent, so the probability of the intersection of two events just equals the multiplication of the probability of each. So in other words, we can see, there's the equation is a symmetric in E and F, right? So E and F are independent with each other. So definition, two events E and F are said to be independent, if this equation holds, if the probability of the intersection equals to the product of their probabilities. So two events E and F that are not independent, so it's dependent. What is it? It's the conditional probability. So let's see example 4a. A card is selected at random from an ordinary deck of 52 playing cards. If E is the event that the selected card is an ace, and F is the event that it is a spade, it could be, so E and F, it could a spade and it's an ace, so those are two different events, right? Ace count the numbers, spades count the suit. We have 4 suits but 13 numbers, so those two events are independent. Then E and F are independent. This follows because P of E and F equals 1 out of 52. So what is the intersection of E and F? It is a spade, it's an ace in spade, right? And there's only one. There's only one ace in spade. And the probability of E, well, E is ace. How many aces we have in the deck of 52 cards? 4 of them, because we have 4 suits. Okay, so maybe some of you haven't played any cards yet. The 52 cards, we have 4 suits for different kinds of 4 suits, and I have each one has 13 numbers. So we have 4 aces, so that's why probability of ace is 4 over 52. And the probability of F is a spade, right? We have 13, we have, no, what I'm talking about, yes. F is a spade card, spades has 13 numbers, and that's 13 out of 52. So we see those two are independent. Right, so this is independent 2 events. Let's see for B. 2 coins are flipped, and all 4 outcomes are assumed to be equally likely. If E is the event that the first coin lands on heads, and F the event the second lands on tails, then E and F are independent, right? Because we toast the first one, we toast the second one. The probability of E intersect with E, or E and F, is the probability of getting heads or getting tail is 1/4, 1/4, right? Getting the first one to be a head, getting the second one to be a tail. What is our sample space? Our sample space is HH. The first one is head, second one is head. Then HT, first one is head, second is tail. The third one is the first one is tail, second one is H. So it will be TH, then TT. So we have a sample space of 4 members. So this is 1 out of 4. That's why the probability is 1/4. Right. So probability of even E. Yeah, the first coin again lands on head, second lands on head. So we have the first one lands on head, but the second one also lands on head, or the first one lands on head, second one lands on tail, on the tail. So we have, so that's half. While F lands on tail, we have first one lands on head, second one lands on tail, or both of them lands on tail, also half. Any questions? Okay, let's see C. Suppose we told the 2 fair dice. Like E1 denotes even the sum of the dice is 6. Right, we told 2, and the sum of the face value to be 6. And F is the event, the first die equals to 4. Then probability of E1 intersect with 4, or E1 and F. E1 and F. So the sum of the 2 dice is 6, and one of them is 4. So what do we have? We have 4. So the first one is 4. Well, one of them is 4. We could call the first one is 4 because the sum, we really don't care which one is 4. 4 or 2, there's 1 out of 36. Yeah. Oh, it is constant. The first die, it says the first die equals to 4. Otherwise, if we don't care about which die is 4, that would be 2 out of 36 because we have 4, 2 and 2, 4. Because the sample space is 36, right? Because the first die can have 6 outcomes. The second die has 6 outcomes, so 6 times 6. The sample space are 36 members. And to have the sum of the face value to be 6 and the first die to be 4, that's the probability is, because there's only one of them. So 4, the first die is 4, then 4 is the second one to be 2, because the sum has to be 6. So there's 1 out of 36. Then let's calculate the probability of the product. The product of the 2 probabilities, because sometimes we cannot tell if the events are independent. So what do? We calculate the probability. We calculate the probability of the intersection of those 2 events. Then we calculate the product of the 2 probabilities. So probability of E1 is a sum to be 6. So how many of them? It could be 1, 5, 2, 4, 3, 3, right? So that's a 3, but we could also have 2, 4, and 5, 1. So the 2 more. So the 5. So 5 of them. So 5 outcomes for the sum of the face value to be 6. So that would be 5 out of 36. Then probability of F is the second one lands on tail. What I'm talking about is that the first die, the face value is 4, because each die has six sides, right? 1 up to 6. 1, 2, 3, 4, 6. Because 6 has 6 face values, 6 outcomes. So 4 is one of them. So that's 1 over 6. If we multiply those two, we get a 5 over 216. What's the conclusion? Those two probabilities does not equal to each other. So the conclusion is E1 and F are independent. Are not independent, are dependent. Right? So E1 and F are not independent, because this proves that, because the probability of E1 and F equals 1 out of 36, but the probability of E1 multiplied by probability of F equals 5 over 216. So 4.1 is not satisfied. Independent events satisfy this equation. So 4C does not satisfy the equation, so those two events are not independent with each other. Well, we can find the reasons why in 2.0. Now I can highlight. The reason for this, because we are interested in the probability of throwing 6 with 2 dice, the sum value is 6. We should be quite happy if the first die lands on 4. However, the first die lands on 6, right? Because there cannot be sum to be 6. Anyway, let's see this one. This one is saying, now let E2 to be the event sum of the dice equals to 7. Is E2 independent of F? Because F is the first one to be 4. Right? So if the first one is 4, then the second dice, the face value has to be 3 to be able to add up to 7. Then the probability of the intersection of E2 and F is 1 out of 36. Now let's calculate the probability of E2. Right? How many? So let's calculate. Maybe I'll put in the chat. So let's see how many we have. We have 1, 6. Okay. Just put a set value here. 2, 5. Then we have 3, 4. Then we have 2, no, what did I do? 1, 6, 2, 5, 3, 4. I should do 4, 3. Then 5, 2. Then 6, 1. We have 1, 2, 3, 4, 5, 6. So we have 6 of them. Yeah, 6 outcomes to add the two face values to be 7. So that's 6 out of 36 is 1 over 6. Right? So that's why probability of E2 is 1 over 6. So this is different from this. Adds up to be 6, we only have 5. So 1 over 6. The 1 over 6 times 1 over 6, so probability of F, right? It's 1 out of 36. Right? So you can think about the why. You know, when the face value equals 7, it becomes independent. It's very interesting. Any questions? You can also, so one thing you can also do is you make a table, right? You make a table with 36 grades. Then you put numbers in it, 1 up to 6, horizontally, 1 up to 6 vertically. And then you can count the face value. You add up to different numbers, and certain of them are independent, and some of the events are not independent. Very interesting. Okay, let's see this example. If we let E denote the event that the next president is a Republican, and F the event there will be a major earthquake within the next year, then most people would probably be willing to assume that E and F are independent. Yes, I will do that. Who is the Republican to be a president, or the earthquake seems to have nothing in, no relation at all. However, there would probably be some controversy over whether it is reasonable to assume that E is independent of G, where G is the event that there will be a recession within 2 years after the election. So if E is independent of F, then E is also independent of F complement. Okay. Let's see that. Let's see why. So if E and F are independent, so are E and F. So what do we do? So we need to calculate the probability. We want to use this one, right? I don't know why I cannot highlight on this page. So we want to use the equation 4.1. So whenever we want to prove that two events are independent with each other, this is the equation we want to show. All right, this is the equation we want to show. So let's see this. So we want to prove probability of E and F complement, and F complement equals probability of E multiplied by probability of F complement. Well, let's do that. So probability of E equals the probability of E and F plus probability of E and its F complement. So probability E and F, we know those two are independent because this is a given. We know those two are independent. So this one equals the probability of E multiplied by probability of F. So we need to find this. Well, what is this? So this equals the probability of E times, well, we just move this one to the other side, becomes minus, right? So we have a P probability of E minus probability of E multiplied by probability of F. So we factor out probability of E. Then inside parentheses, we have 1 minus probability of F. Well, what is 1 minus probability of F? Probability of its complement. So indeed, so 4.1 equation is proved. So that's why even if two events are independent, and one of the events will be independent of its complement. Let's see this example. No, this is no good. What's wrong with this? Let's see if we can do this. Two fair dice are thrown. Let E denote the event that the sum of the dice is 7. F denote the event that the first die equals 4. Okay, it's similar to the previous one. And and the event G denote the event that the second die equals 3. From example 4C, we know that E is independent of F. And the same, I guess it says the same for G, right? Same for G. So E has been proved from the previous one. So the same for G, because G denotes the second die to be 3. If you think about it, if the first die, the sum of two die is 7, and the first die is 3, it forces the second one to be 3. So if we're treating G as the second one equals 3, it forces the first one to be 4. So G and the E are like a complement. Like G is a complement of E. So if E is independent of F, then G has to be independent of F also. I guess that's the question. Let's see. Oh, we're missing A. Okay, but we have a solution here. In order to determine the probability of at least one success. Oh no, this is missing many pages. Or missing page 2. Okay, let me reload this. I don't know what's going on with this. Let me try one more time. Let me see. I don't know what's going on because I saved on my Google Drive. Sometimes my Google Drive give me a problem. Okay, are you trying to help me? Oh, I think this time should be okay now. Okay, it looks good this time. Oh, someone can share this video. Let me try one more time. If not, you can share yours. Thank you. I know you're trying to help me. Oops. Okay. Oh, I thought I hit it to the page. Let me just go slow. Yes. Yes, here, okay. So let's just remember those two events. So the sum of two dice is 7, and the first event is the event E is the first die is 4, event G is the second die is 3. So we want to show E is also independent of G, but clearly E is not independent of F and G. Since probability of E given FG, F intersected with G. F intersected with G. So F is the first one to be 4. G is the second one to be 3. Well, F intersects G with it's 100%, right? Because those two needs to add up to be 7. It would appear to follow that example for E that probability definition for independent 3 events would have to go further than merely assuming that out of 3 choose 2 pairs of events are independent. Okay. Okay, so this basically introduces G as the third event. All right, let's see the definition. So we have 3 events. If they are independent from each other, that means the intersection of those 3 events, the probability of the intersection of the 3 events equals the product of the probability of 3 events. Then also means probability of E and F equals to the product of those two. Probability of E and G equals to those two. Probability of those equals to those two. Okay, this is a definition, by the way. But definition, we just don't have the proof. If we define this way, okay, we define this way. If this is true, if this equation is true, then we say, okay, the 3 events are independent. So if E, F, G are independent, then E will be independent of any event formed from F and G. For instance, E is independent of F union G. Since, let's say that. So probability of E intersect with F union G is the probability of EF union probability of EG E and G. So that equals, so probability of union equals the probability of EF plus probability of EG minus the intersection of those three. And probability of those two, because they're independent, equals those two equals those two. And probability of this equals the probability for this. Then, so this is probability of E and probability of G. So this has a probability of E, so we can factor out the probability of E. All three has a probability of E in it. So we factor out, we have probability of F plus probability of G minus probability of F and G. Oh, what is that? That's a union, right? So this three shows the union. So this three is a union of probability of F. So probability of F union G. So we can extend this to finite many events. So we define an infinite set of events to be independent if every finite subset of those events is independent. Okay, if each sub-experiment has the same set of possible outcomes, then the subset experiments are called trials. Let's see example for F. The infinite sequence of independent trials is to be performed. Each trial results in a success with probability P, and a failure probability, of course, is complement 1 minus P. What is the probability that at least one success occurs in the first n trials? B, exactly k successes occur in the first n trials. All trials result in successes. So for at least one success in first n trials, it's easiest to compute the first probability of the complement event, that of no success, right? Because whenever we see at the least, at the most, stuff like that, we prefer to find its complement. So we want to find its complement, which means no success in the first n trials. So if we let EI denote the event of failure on the IS trial, then the probability of no success is probability of no success equals the multiplication of all those probability of those n events. And each one is 1 minus p, and then we have n trials, so it's 1 minus p to the nth power. And then, so to the answer, at least one success is 1 minus p to the nth power. To compute B is the exact k successes in n trials. So the first n outcomes containing k successes and n minus k failures. So each one of those sequences will, by the independence of trials, with the probability of p to the k's power, right? Because the probability of p, and then we have k successes, so p raised by k, and the rest of it is 1 minus p to the n minus k's power, failure, right? 1 minus p, failure. Success and failure has to be independent. They're complementary with each other, right? If two events are complementary with each other, they must be independent of each other. So we have p to the k's power, 1 minus p to the n minus k's power. And here we could think, why we have 1 minus p to the n's power? Because you could think this is 1 to the first power, and 1 minus p to the n minus 1's power, n minus, 1 to the first power. This is at least one success, right? We have no failure, at least one success. All right, so this is k successes n minus k failures. So out of n, choose k is n factorial divided by k factorial divided by n minus k factorial. So the desired probability for part B for exactly k successes, probability of exactly k successes is out of n, choose k, right? Because we have n trials, we have k successes, out of n, choose k. And p to the k times 1 minus p to the n minus k's power. This looks like what? Binomial theorem. Binomial theorem, right? Okay, to answer C, C is saying all trials result in successes. So the first n trials, all result in successes is given by probability of E1 complement, E2 complement, up to n's complement. Because failure, right? Successes is a complement of failure. So successes equals the p, the probability is p, so the p to the n's power. Because we have p of E1 complement E2 multiplied by p probability of E2 complement until probability of En complement. And everyone has a probability of p, so the p to the n's power. Anyone has any questions so far? Okay. Okay, so probability of the intersection of all those successes, because is what? Is the probability of, oh, this is going to infinity now, right? So the above is for finite many, right? For k successes, for at least one successes. Now we're going to infinite sequence. Infinite sequencing, you know, all trials result in successes. So this is saying probability of all trials has successes, and the infinite many equals the probability of taking limit, because we always do this, right? We're going from finite world to infinite world. What do? We make a dummy variable n, then we use a limit I dummy variable n run to infinity. Right? That's one of the mathematical trick. We need to know how to use it. Yes, anyone has any questions? All right. So the limit inside, and we can take out the probability, right? Because the limit, if the limit exists, the limit is a real number. And if probability exists, probability is a real number. So what we can do with a real number, we can do here. So you can take a limit outside, then we take a probability of all this intersection, which we know is this, right? Which we know is this. So it's p raised by n. So what's the limit? P raised by n when n runs to infinity. It says either 0 if probability is less than 1, or 1 if probability equals to 1. Because n goes to infinity. Okay. Let's see this example. A system composed of n separate components is said to be a parallel system if it functions when at least one of the components functions. For such a system, if component I, which is independent of the other components, functions with probability pi. So there's I equals 1 up to n. What is the probability that the system functions? So we denote the AI as the event of component I component functions. Then probability of the system functions, because at least one is function, so we consider a functions, equals to 1 minus the probability of its complement. Its complement means the system does not function, which is the contrary of at least one component's function, which means non-component functions, right? Non-component function, or all components do not function. None of them functions. So that is the probability of intersection of all its complement. And that's a 1 minus pi. So this is a product. Okay, this sign is a product. So 1 minus pi, because we don't know the probability, because the ith component may have different probability than the next one. So each component has a probability of success of functions differently. So we use this product sign. This means 1 minus p1 times 1 minus p2 times 1 minus p3 up to 1 minus pn. So which is 1 minus the product of all those. Anyone has any questions? Okay. Let's see this one. Independent trials consisting of rolling a pair of fair dice are performed. What is the probability that an outcome of 5 appears before an outcome of 7 when the outcome of a roll is the sum of the dice? Interesting, huh? So what is the probability that the outcome of 5, the sum, considering the sum? So we're rolling 2 dice, we're considering the fifth value, the sum of the 2 fifth values. So what is the probability that an outcome 5 appears before an outcome of 7 occurs? Let's see. Let En denote the event that no 5 or 7 appears on the first n-1 trials, and a 5 appears on the nth trial. Then the desired probability is, what about the 7? Okay. Is the probability union of all those ENs, union of all those trials equals to the sum of the probability of each one. Right? Because again, each trial is independent, right? Each trial is independent, there's no intersection. So now, since the probability of 5 on any trial, right? So 5 appears on the nth trial. Probability of 5 on any trial equals to 4 out of 36. 1 and 4, 2 and 2. No, 1 and 4, 2 and 3, 2 and 3, 3 and 2, 4 and 1, right? Yes, 4 out of 36. Then probability of 7 on any trial will be 6 out of 36, right? Sum to be 7, we counted before, there's 6 of them. So we have probability of En, the nth trial, have no 5, no 7, is 1 minus 10 over 36. Because we add those two, probability 5 on any trial, probability of 7 on any trial, and probability of 5 or 7 on any trial will be 4 over 36 plus 6 over 36, which is 10 over 36, right? And no 5 nor 7 appears would be the complement, would be 1 minus 10 over 36. And on the n minus 1 trial, right? So that's interpretation of this. No 5 nor 7 appear on the first n minus 1 trials. So get this. Then, why we multiply 4 over 36? So probability of En. Oh, what about the rest of it? Because this is n minus 1, right? We still have n, the last one, which is a 4 out of 36. Right? The probability of happens on the nth trial. Probability happens on the nth trial. On the nth trial, right? We still have four some value to be 5 out of 36. So hence now we can use this one, right? So we have probability of En now, and we put in, we have a sum of that. So 1 minus 10 out of 36. We can simplify to be 13 over 18, because which is 26 over 36, simplify to be 13 over 18, and minus 5. Well, 4 out of 36 can be simplified as a 1 over 9, because 1 over 9 has nothing to do with n, because the index is n, so we can put a 1 over 9 up front. Then we see this is, what is this? Vector, not vector calculus, calculus 2, right? Calculus 2, infinite series. So infinite series, and this is a geometric series. Geometric series, we have and because this 13 over 18 is less than 1, so we can calculate this geometric series, which is the first, which is the number, well, this is 1, or we can put 1 over 9 here. If we put 1 over 9 inside, right, that will be 1 over 9 in the numerator, we consider as the first term. Then over 1 minus this r, right? In geometric series, we call this r, 1 minus this r. So 1 minus 13 over 18, we calculate, that's 2 out of 5. Isn't this amazing result? Right? Isn't this amazing result? So this result could also have been obtained by the use of conditional probabilities. If we let E be the event, a 5 occurs before a 7, then we obtain the desired probability of this by conditioning on the outcome of the first trial. So, okay, so we could do this also. Let F be the event that the first trial results in a 5. Okay, that yes, because we want the 5 appears before 7. And G be the event 7. Right? Then H be the event that the first trial results in neither 5 nor 7. Then conditioning on this, which, so we have probability of event E, okay, equals to probability of E intersect with F, probability of E intersect with G, probability of E intersect with H, right? Then probability of E intersect probability of E given F is 1, because F is the event 5 occurs before 7, right? So basically, okay. Then probability of E given G, well, G is an event that's say 7, result is 7, right? If 7 appears before 5, so that's 0. Then probability of E given H, H is an event in neither situation, you know, neither a 5 nor a 7. So it has nothing to do with the situation 5 appears before 7. So that's the probability of the whole event E, which is right? Because H, if H, because this H is neither 5 nor 7. So that would be probability of E, because the probability of E is 5 occurs before 7. So these two events, right? These two events. So then the first two equalities are, the third follows before if the first outcome results neither 5 nor 7. The childs are independent. So probability of F is 4 out of 36. Probability G is 6 out of 36. Probability of H is 26 out of 36. So we just plug in those numbers. We get the same result. Okay, so this shows us the two ways to solve this problem. But I think the first way is really cool. I think the first way is really cool because it uses the infinite series. Okay, anyone has any questions? I'm going to stop right here. And next class, next class maybe we'll talk more about the examples. Oh, this is cool. This is going to use the multinomial coefficients. Okay, this is cool. This is a classic one, the gambler's ruin problem. Okay. Okay, cool. We even have a graph. All right, let's see. So this book is totally new to me as a new to you. But up to which question? You mean for the example? For the example, we're up to for I. Example for I. Okay, guys. Keep up your good. Have a good night and have a good weekend. All right. Thank you. Have a good night.